Good afternoon, everyone. Welcome to the fourth in the ACENET Basics series of webinars for 2017, Understanding the Grid Engine, Job Submission and Scheduling at ACENET. If you are taking this in via the video software, VIDYO, you may be able to interact with us by using the little raise hand icon at the bottom of your screen. However, you can also rest assured that when we get to the end of the talk, we will enable text interaction and audible questions, whichever you prefer, at the end of the hour. My name is Ross Dixon, and the topic today is the job scheduler, Grid Engine. If you happen to take in some of the earlier talks in the ACENET Basics series, then the first few slides will review. If you didn't, don't worry. You haven't missed anything critical. The first key thing to know about job scheduling is what a job is. A job script is just a shell script, which is, say, one or more lines of commands that you could type at the command line, bundled up into a file, and then submitted to the job scheduler with a command qsub. On this slide, the thing outlined in the red rectangle is the job script. The one line of execution is we want to run my program, and we want to take the input from an input file called some input file. And then there's three more lines at the top in this example, all starting with hash mark $, and various obscure things. These are directives to the job scheduler. These are not executed while the job is running. These give the job scheduler information about what it needs to do. The particular job scheduler that we use at ACENET is called Grid Engine, or once upon a time Sun Grid Engine. Other high-performance computing installations may use other job schedulers with names like PBS, or Torque, or Moab, or LSF, or Load Leveler, or Slurm, or probably a few others I haven't thought of as well. And they all work on similar principles to what I'm going to describe to you today. The precise syntax is going to vary. So the syntax I'm showing you has to do with Grid Engine Job Scheduler at ACENET, but the concepts are transferable to other job schedulers at other HPC institutions across Canada and around the world. So you have your Grid Engine job script with these directives, which I will explain more about in a few slides. You type qsub, the name of the file, and the scheduler comes back with your job, some number, the name of the file has been submitted. This number is a unique job ID identification number, job ID number. And it plays a pretty important role, particularly if you run into any sort of troubles and we have to start troubleshooting your jobs. So it comes up here. You'll see it come up again a few times here and there. So once you've typed qsub, then you want to know how your job is doing. The next command you need is qstat, Q-S-T-A-T. You type that, and if you happen to have your screen set narrow, then you may find that things come out a bit of a jumble like they're shown on this slide. In real life, well, I don't know, our computer's real life. If I submit a job like this and type qstat, it should look something like this on your screen. But you'll notice that I've got the resolution on the screen turned down really low, and that's really wide. That's something like 116 columns of width there. And so if you have a narrow screen, they may get jumbled up. Nonetheless, you'll be able to figure it out. The key things to be noted here are, first of all, over here we have that job ID number that I just mentioned as so critical, shows up when you type qstat. The name of the job, which by default is also the name of the job script file, is there. And then here we have something called state, and that's the field you're probably most interested in because that tells you, is my job running yet or is it still waiting? If the letters under state are QW, that means it's waiting. Don't ask me what the Q means, I have no idea. If the letters there are R, I see my job has started running now. And then it tells you when you submitted the job if it isn't scheduled yet, or when it started if it has been scheduled and is running. If it is running, it also tells you a little bit about which node of the cluster it's running on. And over here, it notes how many different processes you are. If you're running parallel jobs with multiple processes, then that's what shows up in the slots column. So we may use the term processes, slots, or even cores interchangeably here. We're all talking about the same thing in this context. And if you see nothing at all from QStat, that means you don't have a job in the system. So if you only submitted one, that probably means your job is finished. Let's see if we're there yet. Yes, my job is finished. Now, about these signifiers with the hash mark $sign in front of them. Those do a number of jobs, but the most important job they do is that's how you tell the job scheduler what resources you need. If you're going to be running some sort of calculation, obviously you need at least one CPU core. By default, if you don't ask for anything, you get one. CPU cores, runtime, and memory are the three main things. CPU cores default to 1. I'll show you how to ask for more in a moment. Runtime has no default. This is a policy decision we made at ACENET, and it's reflected in a number of other places outside ACENET as well. You have to tell us something about how long you expect the job to run. The parameter is h_rt, and it's supplied with a prefix -l, space h_rt, and equals something in hours, :minutes, :seconds, or you can just give straight seconds if you like. And the H here stands for hard. This is a hard limit on runtime. And by hard, we mean that after the job starts running, it goes for as long as h_rt that you've asked for. And if it hasn't finished by itself by then, if the calculation hasn't stopped and the script exited, all great. If it's still running, then the scheduler will kill the job at the point that HRT expires. So that's why it's important that you leave some sort of margin of error on your estimate for h_rt. The other thing that I'll point out with this slide is that there are two ways of specifying the hard limit on runtime. It's always with h_rt, well, -l, h_rt. But you can put it in the script, like I showed a couple slides earlier, with the $sign introducing the line, and then -l, h_rt equals whatever. Or you can supply it as an option to the qsub command when you type the qsub command. So you can say qsub -l, h_rt equals 1 hour, 0 minutes, 0 seconds, name of the script file, and whatever other arguments might be relevant. This is general. All of the directives that I show you in this talk about Grid Engine can either be supplied inside the script with the introduction of the $, right at the left-hand margin, or they can be supplied on the command line as arguments to qsub, like this. If you supply it both ways, and if there's a contradiction, then whatever you supply to qsub overrides whatever is inside the file. This may be useful, for example, if you're troubleshooting and you have got your script set up and you expect to run for 48 hours, or expect that you've supplied a runtime limit of 48 hours, say, but you're troubleshooting, something's going wrong, you're submitting quickly to try and just get the thing to fail, because usually if something goes wrong, it goes wrong in the first minute. So you can leave your script with a 48-hour runtime, but you can do qsub -l, h_rt equals 5 minutes. And it will hopefully fail in the first 5 minutes. This will come up again later on. So you must ask for runtime. That's by policy. If you don't ask about CPU cores, you get 1. If you want to run parallel programs, then you need to ask for more than 1 core, or you're not doing yourself any good. The way you do that with Grid Engine is by use of a parallel environment. And so the directive here is -pe, and then the name of some parallel environment, and then the number of slots or cores or processes that you want. For example, -pe OMPI*4. And OMPI* is the name of a parallel environment. The three most frequently used ones at ACENET are OMPI star, OpenMP, and Gaussian. OMPI star is for distributed memory parallel computing. That is to say, parallel computing with MPI. And if you don't know what that is, don't worry about it. If you do know what it is, this is the parallel environment you want. The next most common one is OpenMP, which is for shared memory parallel computing. With OMPI star, if you ask for 16 processes, those processes may be started on one machine or on 16 machines or in anything in between. The processes can be spread arbitrarily across machines. If you're doing shared memory computing, that won't work. You need all the processes to be on a single machine, and so the OpenMP parallel environment means that all the processes you asked for get started on a single machine. Because we have no machines at ACENET larger than 16 cores, asking for OpenMP 16 is as large as you can go with shared memory at ACENET right now. You can only ask for 16 slots with OpenMP. And there are various other parallel environments. Gaussian is a particular custom parallel environment for a particularly popular computational chemistry package, and there are a few others that you can read about on our wiki if you really want the gory details. So time, CPU cores, the third major thing that you're going to need to ask for is memory. And here again, we do provide you with a default. The default amount of memory you get is 1 gigabyte or 2 gigabytes per parallel slot, and that depends on which cluster you're on. You can look it up on our wiki. I'll emphasize that these are numbers per slot. So if you're doing parallel computing and you're using a parallel environment, OpenMP or OMPI star or Gaussian or anything, and you're asking for memory, you're asking for the amount of memory you want per slot. So if you want a 4-slot job and you ask for 4 gigabytes of memory, you're going to be getting a total of 16 gigabytes of memory. We insist on managing and limiting memory because on HPC systems, well, on every computer in general, but HPC systems suffer from this particularly badly because they're shared systems with a lot of users on them. If you have a bunch of processes running on a single one of our compute nodes, and between them they exhaust all the physical memory there is on that machine, they use up all the RAM, they may keep going because they can do a thing called swapping. But what swapping does is it starts to use the hard disk on the machine as a backup for the random access memory. And the hard disk is so much slower than the random access memory that the performance of your code may drop by a factor of 10 or 100. And we have measured this. It can be that bad. This obviously makes complete rubbish of any runtime estimate that you supplied or the other users using the node supplied. And so that's why we enforce limits on memory. 1 or 2 gig per slot by default. You can ask for other numbers. Most of our machines have about 4 gigabytes available per slot, although there's a great deal of variance there because we've got quite a bit of different hardware at our 4 different clusters. And the specification here is -L H_VMEM. It does understand things, the usual suffixes like G for gigabytes and M for megabytes. Gigabytes is usually the way you'll be thinking of these things. And the H here, like the H in H_RT, stands for hard limit and runtime. The H here stands for hard limit and virtual memory. If your program tries to allocate more memory than it asked for from Grid Engine, then it will be killed. So those are the big three: cores, memory, and time. And the scheduler's job is to try and figure out how to take your request for cores, memory, and time and fit it in with all the other people's requests for cores, memory, and time for their various jobs. If you're happy with that and you are happy to just submit your jobs requesting the resources you think you need and they run whenever, then you can stop listening right now and go away. The rest of the talk is going to be dedicated to what can go wrong with this. And 3 major classes of what can go wrong are these. Your job may crash. So you submit it, it starts running, sometime later it's finished, and you look at the output and there's no output there, or there's some output there but it stops in the middle. The second major class is that you type qsub and it doesn't even take your job. It gives you some obscure message like error no suitable queues. The third major class is you submit the job, goes into QW wait state, and it's not running, and it's still not running, and it's still not running. So the rest of the talk is going to be addressing these three things in that order, and what you can do about them, and when you should call us for help with them. So, first of these three, my job crashed. What happened? I'm sorry to say, the most likely thing that happened if your job crashed is there's something wrong with the program you're running. There's something wrong with your code or your input, and it's not got anything to do with Grid Engine. So, first thing to do is, have you tested it? Have you tried running the code outside of Grid Engine in a really small test case, preferably one that takes no more than 5 or maybe 10 minutes at tops to run, and you can run it on the head node without using up all the memory there. Try running it outside Grid Engine, just from the command line, doing what you have your job script set up to do, only do it at the command line, see whether it works. Second thing is look at all the output. If you can't find the output, maybe you're looking in the wrong place. If you are using one of our default scripts that you copied off our website or copied from this talk right here, this line at the top here that says -cwd, that tells the Grid Engine that we want to run the job in the current working directory. If you leave that line out, your output may mysteriously not appear where you expect it to. Your output is going to go in your home directory instead of your current working directory, and that occasionally mystifies people. Also, if you're using output redirection, the greater than sign, send the standard output to some file you've named in your script. You may get some stuff going there, but you may get other information going into a file that Grid Engine creates, which is typically got the name of the job, which by default, as I said, is the name of the script, .o, and here's that job ID number again. So there's going to be one of these output files generated for each time you submit a job. Each time a job runs, rather. You can submit a job and it may not run. You can delete it with QDEL. So, make sure you know where all the output is. Oh, and it's also possible for there to be yet another file of the pattern script.sh.e123456, which contains the standard error. Standard output and standard error are two different streams that you may not have heard of on Linux systems before. They're both there, and if you leave out the -j parameter that was shown in that example script, then you will get both a .o and a .e file, and there may be information in this. So there's three. If you don't find your output where you're expecting to, look in 3 different places. Look in your home directory for files that were created there. Look in name of the job .o, job ID number. Look for name of the job .e, job ID number, and see if there's any information in there that tells you what's gone wrong. If none of that's worked, and you've tested the thing in the head node and it works fine, and you can't find any clues in the various output and error files I've just described, then yeah, maybe there's something about what's happening in Grid Engine that is messing up your job. So, just submitting it again and waiting a day or something like that for a very large job to turn around is going to be a ridiculously painful way to do troubleshooting. You should be aware of the test resource. We have typically 1 node, sometimes 2 nodes, 1 node set aside at each cluster for a test resource for just this sort of thing. A test job must have a runtime of 1 hour or less, and you have to explicitly say this is a test job, and you do that like shown on this slide. h_rt equals 30 minutes, which is less than an hour, comma test equals true. The reason for that is that somebody who has 1,000 one-hour jobs doesn't submit them all, and they all use up this test resource, and then you can't use it for the test purpose. So you have to explicitly request test equals true, and the time limit on the test resource is 1 hour. Because we've got it set up this way and carefully fenced off, you will almost always get immediate turnaround. And by immediate, I mean typically the job will start running in 30 seconds to a minute from when you type qsub. Unless it just so happens there's someone else also using the test queue that day to troubleshoot their own thing. It's a rare enough occurrence that this is a pretty reliable resource for testing things. So, tried it out in the command line, worked there, looked at all the output files and error files, no clues there. Try submitting a test job using the test queue and see what happens then. Another option, perhaps a little bit less attractive, is that you can also try an interactive job with Grid Engine. So instead of running the script, what you want to do in this case is you want to get a command line session with the shell. Bash is the name of the shell that I've been teaching people about. Get a command line session on one of the compute nodes. And this will have pretty much identical environment to what your job script would have, but you're interactive and you can do things like look at environment variables and try out commands and all that kind of stuff interactively. The downside here is that this, well, if you can ask for test equals true, and it will go to the test resource that I was just describing, so that's a good way to go. If you want longer runtime, you don't have to ask for test equals true, but in either case, if the resource is busy, if there's no way that your job can be scheduled right now, then you get rejected and you can't do that right now. But there's no waiting around to find out. If that doesn't work, then drop back to the previous slide, test jobs, and just submit the script. So interactive jobs are possible. You'll note that the command here is no longer qsub, it's qrsh, but the parameters are all the same. cwd says run the current working directory. You need to specify a runtime. You can optionally specify test equals true. And typically you would probably want to specify bash as the in order to start the shell on the interactive node. Another thing that can happen, which does not leave very good traces, and this is a minor flaw in Grid Engine, is that Grid Engine, if it's obliged to kill your job, either because it ran out of time or because it ran out of memory, either didn't have enough HRT or didn't have enough HVMem, then it doesn't leave you a very good diagnostic of that. It doesn't tell you explicitly in the output of the error file, oh, I killed your job because you asked for too much memory, or I killed your job because it ran out of time. So you've checked all the previous things, the output's just truncated somewhere, or it doesn't even get started, what's going wrong? Possibly it ran out of memory. This is a fairly common thing. We have a utility that you can use to probe this. So you need to save that job ID number. Here's a job ID number. And you can run probe SGE logs on the job ID number. And maybe, if memory was the problem, it will show you a message like the one shown here. The key phrase is exceeds job hard limit HVMem. And that tells you that what you should do is try submitting it in with a larger HVMem, add a gigabyte maybe, or consult with us via support@acenet.ca if you want some advice over what you ought to do. But the simple thing there is just use a larger HVMem, see what happens the next time. So those are, and if none of these things work, obviously, then what you do is you write to support@ace-net.ca and tell us, okay, my job crashed, why? We're going to want to know what that job ID number is, or several of them. If you've done this several times, tell us what the job ID numbers are. And we're also going to want to know which cluster you were on. We have 4 clusters. Don't make us guess which one to look at first. It's a little quicker if you just tell us it was job 34162444 on Fundy. I also tried, 6243, 6242 were the same. I tried these different things. Here's a copy of the job script. Here's the job ID number. What can you do for me? So that's crash jobs. On to problem of the second type. You type qsub, and it says, unable to run job, error, no suitable queues, exiting, which is a really useless error message. What that means in English is that Grid Engine thinks it's never going to be able to schedule this job. If you fail to supply a runtime, h_rt, you will get this message. So first thing to check, did I actually have an H_RT in there, and is it properly formed? You may also get it if you ask for an impossible amount of some resource. We don't have any nodes on any ACENET cluster with 256 gigabytes of RAM, for example. So if you ask for a single process job with 256 gigabytes of HVMEM, it'll say no suitable queues. We don't have any clusters with 6,000 CPU cores. So if you ask for a parallel environment with 6,000 slots, it'll say no suitable queues. More typically, and perhaps more subtly, you may be asking for some impossible combination. So maybe we've got 1,000 cores in this cluster, and maybe we've got some 128 gigabyte machines, but maybe we don't have 1,000 cores that all have 128 gigabytes per core. Actually, we certainly don't. I can guarantee we don't. Or maybe even because there are some time policies that I'm going to talk about in future slides, it may be that we have machines with enough memory and we have machines with enough cores, but by policy we can't let a job of 720 hours run on it, for example. So if you get the error no suitable queues thing, first check your HRT, then check to see whether you've forgotten that memory is requested by slot and you've asked for 256 gigabytes in total when really what you wanted was 4 gigabytes per core and a what is that, a 64 core job or something like that. Third thing that can go wrong. You've submitted your job, it's there, it's not running. Well, look at QStat. I already showed you R for running and QW for waiting, but you can see other things there. One of them that you may see is EQW, capital EQW. What that signifies is the job has gone into an error state, which is a little odd. It doesn't mean that your program has crashed. It means that the script itself had some trouble getting started. Now, perhaps the most typical, and you can get a clue actually to start off. You can get a clue by running QStat with the -J flag, which I haven't shown you before, and that job ID number again. So QStat -J 7654321, whatever the job number is, and look for the line that says error. And if you took in the shell scripting talk, you'll know the way you can do that is to use the pipe character vertical bar and then grep for error. In any case, QStat -J and the job ID number, and look for the lines that have the word error in them. And it may say something like unable to open output file /home /John Doe / whatever, whatever, whatever. Did you tell Grid Engine to send the output somewhere that doesn't actually exist? Did you submit the job from a directory and then change the name of that directory after you submitted the job? Are you working closely with other members of your group and you submitted a job from a directory where you don't actually have permission to write, for example? All these things can happen. Another thing that can happen, if none of those seem to fit the bill, then again, write us at support@acenet.ca and we'll look into it, because another thing that can happen is occasionally one node will go a little bit wonky and it'll start doing this to jobs. So if you send us the job ID number in the cluster again, we may look at it and go, oh, right, okay, that's happened because node 99 has gone off the rails. We'll take it offline and we'll put your jobs back in a state where they can schedule again. So that can happen as well. However, if you find that, yeah, you just got an incorrect path or something like that, then what do? Well, you've got all these jobs in EQW state. Really, the simple thing to do is delete them and resubmit them, and that's what I recommend. In case I haven't mentioned it before, the command to delete a job is qdel and the job ID number. I think you can also use the job name there if you like as well, but it's possible for you to have multiple jobs with the same name in the system. So you could delete a whole bunch of them at one time by typing qdel in the name, or you can qdel them individually with the job ID number and then resubmit it. This, in most circumstances, has no effect on the priority of your job. Your job doesn't go to the back of the queue because you deleted it and resubmitted it. Your position in the waiting list is determined by things I'll show you a little later. And when you submitted it, doesn't have much to do with it. There's another command you can use to change the characteristics in the job as well, QAlter, but I'm not going to dwell on that here today. I mention it in passing. So EQW is one reason your job won't start, but now we're getting into the down into the weeds, the more interesting cases here. And which is this, you've submitted your job and it's there in QW state and it's been there for a long, long time. User Rip Van Winkle here, his job has been waiting since 2008. Clearly this is not an acceptable situation. So what's gone wrong for this guy? In order to answer that question, I need to tell you a fair bit about how jobs are scheduled. So here is the basic outline of how jobs are scheduled. And this is fairly general. This is not just Grid Engine. This is the way most schedulers work on most high-performance computing systems. There's all kinds of exceptions and caveats to that, but this is the basic idea. This will get you a long ways. First rule is we don't interrupt a running job. Once a job has been started, we let it run until it ends or it runs out of time and we kill it. Or it gets killed for some other reason like memory. Usually that happens in the first few seconds. But the general rule is don't interrupt a running job. We don't stop someone else's job just to start yours. And conversely, we don't stop your job just to start someone else's in normal situations. Second rule is every waiting job has a priority assigned to it. And I'll talk about where the priorities come from in a little bit. But for now, let's just call that a black box. Your job gets a priority. It has to do with how much of the system your group has been allocated. And then rule 3, when resources come free, which is to say when another job ends and frees up some CPUs and some memory, then the scheduler looks at the list of waiting jobs in order of priority. So it looks at the top priority job and says, do I have enough CPUs and memory and time, although time's open-ended, do I have enough CPUs and memory to run this job now? And if it does, great, it starts that top priority job. But if that top priority job is asking for a bunch of resources that we don't yet have, then it will look at the next one on the list. Can I run it? The next one on the list, can I run it? Because the scheduler's prime directive is we want to keep the system as busy as possible so that we get the maximum total turnover of research, right? If we just took jobs in order, ran them first in, first out, then there'd be a lot of idling. We wouldn't be able to efficiently use these things. So, highest priority job that can be run is run, and the scheduler goes through basically all the waiting jobs and all the available resources until it's done the best it can. And then it stops, and in another 20 or 30 seconds, it checks again, are there new jobs that have been submitted? Are there old jobs that have finished? Can we schedule some new stuff? Like I said, it tries to run on about a 20-second cycle at ACENET. It can slow down from time to time. So that's the basic scheduling algorithm. So if you want to know why your job isn't running, the first question should be, what priority does my job have? And the second question should be, when are there some resources coming available, right? So here's the tool that we've put together to try and answer those two questions. It's called ShowQ. We stole the name from a non-Grid Engine scheduler somewhere. I don't remember where. And it has two sections. The first section is running jobs. Those are the jobs that have already started. And they are ordered by when they end. The one that's going to end soonest is shown first on the list. So you can look at ShowQ, and the top of the list is going to be, okay, there's going to be one CPU come available. You can see I made up this slide 2 years ago in 2015. You can see there's going to be one CPU come available at 7:04 a.m. on the 15th of May. And then one more a few minutes after that, and then at 9:07 a.m., 32 slots will become available, or possibly sooner. Because you see, what we do to get these ends by times is we add the h_RT, the hard limit on runtime that you, the user, supplied. We add it to the start time of the job. But remember, most jobs don't actually run all the way to their hard limit on runtime. They actually finish sooner because you give it a safety margin, right? So this is the worst case here. Sometime before 7:04 a.m. on the 15th of May, this slot is going to come free. At worst, we'll kill the job at 7:04 and 31 seconds, or 32 seconds. But most likely, sometime before this hour, these 3 slots are going to come free. And then sometime before this hour, these 32 slots are going to come free, and so on, and so on. The second section of show queue answers that priority part of the question. So the second section has all the waiting jobs ranked in order of their priority, with the top priority one at the top. So this user Crunchy here is asking for 100 CPU slots, and it was just submitted on the 13th of May, but because of their group's priority, it goes to the top of the list. There's complicated stuff there. We'll come back to that briefly. And if your job's a little further down the list, then it should show up there somewhere. And you can see how many cores each of these people is asking for, and you can see the run times they're asking for. The second thing that people often want to know is not when a resource coming free and where's my job stand in the priority list, but just how busy is the system overall. For that, we have another tool called QSum. It also has 2 sections, coincidentally. The first one tries to give you a view of how many of the processors in the system are in use, how many are available for use, and how many are down or unavailable for some other reason. And this is divided up into chunks, all with names ending in .q. These are what we call queues, and I'm going to define them in the next slide. So the first section tries to give you a bit of an overview of how busy the system is. You can look at the available column and get some sense for how many slots are not actually running at the moment. Down below is a sort of a generalized overview of how many people are waiting to use the system. So the key thing down here is how many CPUs are there in the waiting section of the bottom piece of QSum. And by the way, your job, if your name is M. Palin, then great, you've got 62 cores running in 4 different jobs. But your 5th job is not waiting. It's over here in the other error column. It might possibly have gone into that error state EQW we talked about earlier. So if you run QSum and see your name beside other error, you should check and make sure you know what's going on. So what are these queue things? They're divisions of the cluster. Unfortunately, it's a jargon term. It's a technical term with a specific meaning in this specific field of schedulers. If you were taught English anywhere in the former British Empire, you probably think of queue as a waiting line, like the lineup for security at the airport is a queue. If you had a computer science course somewhere in your education, then you may possibly think of a queue as a first-in, first-out data structure, which is closely related to the waiting line at the airport. It does basically the same thing. Neither of those meanings apply in Grid Engine, and I have no idea why they chose to use the word queue. What a queue really is in Grid Engine is it's an abstract software container for a job that's running. Perversely, jobs that are waiting are not in any queue. It's odd, but that's the meaning of the term that they've used here. Once a job is running, it is assigned to some queue or other. The queues, these abstract containers, have finite size. So, for instance, the thing called long.queue at Mahone might have 24 slots available. And it's not exactly a group of compute hosts, but it's pretty close. It's possible for a compute host to belong to 2 different queues. But for your mental model of what's going on, you can think of a queue as being a partition. In fact, other schedulers use the word partition for the same concept. You can think of a queue as being a chunk of the cluster that is assigned to jobs with certain characteristics. The characteristic at ACENET is runtime. So the 4 major queues that you should know about at ACENET are short queue, medium queue, long queue, and test queue. I've already told you a bit about test queue, although I didn't call it by that name. I call it the test resource. Less than 1 hour runtime, and you have to say test equals true in order to get there. The other 3, short, medium, and long, are so named in pretty obvious reference to their characteristic, which say that short queue can take any job with a runtime of 48 hours or less. That should say 48 hours or less, not less than. You don't need to use 475959. 4800 will work fine. Short queue will take jobs of 48 hours or less. Medium queue will take jobs of 2 weeks or less. Long queue will take jobs of a month or less, 720 hours. Obviously, any job that's less than 48 hours is also less than 2 weeks and less than a month. So any job that qualifies to go into the short queue part of the cluster also is allowed to go into medium queue or long queue. You may, if you look at QSum on some of our clusters, see a bunch of other queue names: Martin queue, Tarasov queue, Pomas queue, special purposes queue like Gaussian, Sub, and Tech. Don't worry about these. Basically, these are inaccessible to you unless you happen to belong to a particular research group that has had a custom queue set up for them for some good and valid reason that I won't get into today. So this 48-hour short queue, by the way, a bit of a sidebar, is why when somebody asked me in an earlier seminar this week, if I don't know how long my job is going to run, how do I pick HRT the first time? Well, it's a sort of a bootstrap problem. You have to actually run a job before you know how long it's going to run. But I said, if you really don't know, like you usually have some sort of a clue, 2 hours or 20 hours or 200 hours, you can usually pick which one of those is closest to the truth. But if it's really a problem for you, you're really fresh and have no idea, pick 48 hours. That's after you've run your test job to make sure that your application and your script work correctly. That's what you use test queue for. Once you've done that, when you're up to the production scale and you don't know how long it's going to run, try 48 hours. Those jobs will be allowed to schedule anywhere on an ACENET cluster. If you run out of time in that first one, well, sorry, that was 48 hours wasted, but then we can jump up to a month. It'll take longer for your job to start if it's got a runtime of more than 48 hours because the scheduler wants to keep things busy, and it's got most of the resources dedicated to short queue. So back to the question on the table. Why isn't my job starting? Maybe it's not starting because there are a lot of other users in the system with higher priority than you because of the way jobs have been going lately and because of the allocations of runtime. You can look at show queue to get some idea of where your job stands in the priority list. Maybe you're just asking for slots that aren't there. You've asked for 128 slots for your big parallel job, and there just aren't 128 slots free on the cluster. QSum should show you how many free slots there are. More subtly, maybe there are 128 slots or more, but maybe they're not the right kind. And so if you want those 128 slots, but you've got a runtime of more than 48 hours, you've got a runtime of more than 2 weeks, say, then you need those 128 slots to be in long.queue. And if they're not there in long.queue, then your job's not going to schedule. It's going to sit there in wait state for a long time. So QSum, again, should give you a hint about that. Another flavor of not the right kind of slots is if you're running shared memory parallel jobs with the OpenMP parallel environment, then all 16 of your slots, or whatever number you've asked for, they all have to be in the same host. So there may be 100 and some slots free, but maybe there is no single host that has all 16 of its slots free. QSum can't show you this. We couldn't fit all that sort of level of detail into QSum alone. If you are running shared memory jobs, then you may, and you're curious about why your job isn't scheduling, then maybe what you want is the command qhosts-q, which actually tells you some somewhat useful stuff about the nodes on a cluster anyway. So there's the output from the qhost command. It tells you the list of host names, and the key thing over here is the memtote column, and also the NCPU column. So that's the number of cores there are on each host. That's the amount of memory, RAM, there is in each host. And you should treat these memtote numbers with a grain of salt. That 15.5 gigabytes, really that means 16. This host here will, this host here will take a job of up to 16 gigabytes of RAM. So these memtote numbers, round them up to the next nearest power of 2. 16 gigabytes somewhere down here will have 62.9. Those will take 64 gigabyte jobs. So QHost is there for everybody, but it's probably most useful for people running shared memory parallel if they want to probe these sorts of things. And you can also add a -Q option to it as well, which will tell you about the jobs that are currently running on those hosts. The other thing that can happen is a host may have some available slots. There may only be 2 of the 4 slots taken up, but maybe those 2 slots that someone has taken up have actually consumed all the available RAM. So we had some 4-core hosts with 16 gigabytes of RAM. If 2 of those cores are each using 8 gigabytes, then all the RAM's taken up and the remaining 2 cores are idle. So they will show up in QSUM as if they're available, but they can't actually take a job because there's no available memory. And there's a utility for looking at that as well, memslots, that'll analyze this if you're interested. QHost, okay, I just showed you QHost. Now, I've been waving off this question of priority for a little while. I just said treat it as a black box for now. It's time I got back to that and gave you the real skinny. And again, this is a sort of succession of approximations, really. The basic model is that each project or each research group, each professor's group of researchers, account holders, starts with equal rights to the cluster, so you'll all have equal priority. And then whenever you run a job, that job uses up a little bit of your priority. And it's time decaying. You get your priority back if you stop using the system. It's an exponential thing with a half-life of a month. But what that means is that once you're using the system at high volume, you obviously know what you're doing. You've got lots of jobs in there. Your priority's going down. But the new users who are coming on and trying to figure out, trying to get the job scripts working, trying to get their applications working, trying to just figure out if things are working for them, they have not used the system before. They're going to have higher priority than these large volume research groups. And that's why it's set up that way. The bit at the top about each group starts with equal rights is also modified by things like allocations. Compute Canada's new policy, well, it's not new policy, it's several years old now, is that something like 80% of the CPU time on new Compute Canada systems is going to be actually assigned to allocated projects. So this, every research group starts with equal rights is not a very good first approximation, but that's the design intention of the system. And really what this time decaying thing is going to do is it's going to try and equalize. Occasionally some group will not be using the system because they're off at a conference, in which case other groups should get access to those CPUs. And then when they come back, they may need to make up a little bit of time. So that's how this system works. So down to about 10 minutes left in the seminar, and I'm going to now, I suspect none of you spotted the fly in the ointment earlier when I described to you how the basic scheduling algorithm worked. So suppose, for simplicity, that we have a cluster with only 2 slots. It's a really, really primitive high-performance computing device. Only has 2 slots available. And we have 2 different users, A and B. And A likes to run wide jobs that take up both of the slots. They're doing some sort of parallel programming work, and they need both slots at the same time for their MPI job or their OpenMP job or whatever. And user B runs narrow jobs. They're doing what we call serial farming, which is to say they run a lot of serial or one-core jobs. And B has got a lot of these things. And A just has this one big, wide job, 2 whole slots that they want to run. So B's got a bunch of jobs in the system, and because nothing ever stays regular, one job will start here. This is our timeline. One job for B will start, and then another job for B will start. And the first job will stop, and it'll start a second job in that first slot, and then the second slot job, and so on and so forth. The way the scheduler works, remember, is that when this first slot becomes free here at this first time break, the scheduler looks around and says, okay, I've got job A and I've got a bunch of jobs B. Job A actually has top priority because he hasn't been in the system lately. Job B's been using the system, so his priority is lower. But job A wants both slots, and I only have one slot free right now, says the scheduler, but I can run a B job in there and keep the system busy. So it does that. And then a little later, slot 2 comes free. And the scheduler wakes up and says, A has top priority, but he wants 2 slots, and I've only got 1 slot free, and I can keep it busy if I run another B job. So it does that. And it can do that indefinitely as long as there's some grad student there supplying B jobs forever and ever. This is obviously unacceptable. So how do we get around this? The solution is another scheduler flag called reservation. You introduce it with a $R, and again, you can either supply it as an argument to QSub, or you can put $$R Y for yes inside your job script. And what reservation does is it causes the scheduler if user A with his Y job puts reservation on that job, then the scheduler will stop itself from scheduling more B jobs into this empty slot here, so that it'll save up slots until it has enough of them to put the A job in. And that way A gets to go ahead at something like the earliest possible opportunity. Why don't we just do this all the time to make it fair? Well, 2 reasons. First of all, there's a loss of efficiency. There's this idle time that comes up. We don't really want to be encouraging a lot of idle time. So if we did this for every job, we'd be basically going back to first in, first out, and there'd be a lot of these little idle time spaces in the system. Second thing is doing the calculations for this turns out to be kind of hairy, and it slows down the scheduler. So for both of those reasons, we only do this if you ask us explicitly, which is to say by supplying the -R flag. And by the way, the same argument can also be applied to memory as to CPU slots. So if you're asking for a lot of memory, it may make sense to apply reservation as well. If you are looking at show queue output and your job has been at the top of the priority section waiting, and yet you've seen other jobs bypassing it repeatedly, then possibly you need to turn on reservation. Feel free to talk to us at support@acenet.ca about this. It's not a huge cost to run reservation for a few jobs, but we will not turn it on by default for everything because that will slow things down. So anyway, there's this little bit of idle time here. And that leads us to one final point. I mentioned earlier that if you don't know what the time's going to be, just stick in 48 hours. Everything 48 hours or less gets access to the whole system. Well, if you're astute, you may have said, well, why don't I just, all my jobs are less than 48 hours. I'm just going to set my default runtime limit to 48 hours and never think of it again until I've got my degree. Well, okay, yeah, you could probably get a degree that way and that'll be fine. And I suspect there's some of our users who do that. But here is the carrot. Here is the motivation for why you might want to give us a more accurate estimate of your short run times. If your run times are actually closer to 2 hours or 6 hours or 12 hours or 20 hours, you might want to supply us that number, and here's why. If there is a job in the system with a short enough predicted runtime that it'll fit into this slot here, then the scheduler will do that. It knows it's going to be able, it's planning on running this A job at this time step, but if there's a short little job that'll fit in here, then it will do it. Moreover, the same scheduler logic is used not only when there are jobs reserving, but if we have to schedule an outage. So every once in a while we have to take cluster down to, scrub the file system or do some electrical work or whatever. There's various reasons. We try really hard to make sure that we see these coming and schedule them. Occasionally we get crashes as well. Can't do anything about those. But when we have a scheduled outage, we try and schedule it far enough in advance that we do not actually kill any jobs. So that goes back to, I think, rule 2 of the scheduling algorithm, don't kill any running jobs. We try and schedule our outages far enough away that we don't kill any jobs, but the scheduler then treats that planned outage as a reserving job, like A here. And so as it gets closer and closer to the scheduled outage, the empty slots pile up, because there's jobs that, if we're only 48 hours from the outage, then jobs with a 48-hour time limit will no longer be started. We will not start a job before a planned outage if we know we're going, if it's going to run, if the time limit on it is more than the time between now and the planned outage. So if the planned outage is 47 hours away, we won't start any 48-hour jobs. On the other hand, if you've got 20-hour jobs in the system, then you might be able to get a lot of them done between now and when that planned outage comes, because all these other people, lazy people, have set their time limit to 48 hours. You know yours will get done in 20. You can fit a lot of them in around that planned outage. And some of them will fit in around reservations like this as well, if they're otherwise small. So coming back to the main theme, why won't my job start? Part 5. Perhaps, like I said, if you've asked for a lot of resources, a lot of slots, or a lot of memory, maybe it's being starved, and maybe you should have the reservation flag turned on. Conversely, that also leads to another reason why possibly your job may not be scheduling. This is a special case. We've already sort of covered this by saying, is your job not top priority? Well, okay, your job's not top priority, but it's fairly small and fairly short. I mean, I only wanted one slot for 48 hours. Surely you can schedule that, can't you? Well, maybe there's another higher priority job that's reserving resources. And so back on the show queue screen, how far back do I have to go? Whoops, too far. There it is. Back in the show queue screen here, you can see which jobs have got reservation turned on if they've got a capital R beside slots here. So this user Crunchy with 100 slots is going to have some trouble, because they're asking for a lot of time, they're asking for a lot of slots, and they haven't got reservation turned on. So these slots here are going to go idle sometime around 7 o'clock in the morning or maybe sooner, and his job isn't going to get scheduled. Later on, maybe this job here, 32 cores, is going to finish, and 32 cores will be available. Can't schedule a 100-core job with only 32 cores, so it gets passed over, and maybe some of these other guys slip ahead, because Crunchy probably should have had reservation turned on. Some people ask me where the threshold is. It really depends on a lot of stuff, how busy the system is, how much memory you're asking for, how much time you're asking for. But as a rule of thumb, I don't recommend turning on reservation for anything less than 32 cores. 16 core jobs should probably make out okay. Fred here may be asking for like 8 gigabytes of RAM per core or something outrageous like that, so maybe reservation is a good idea for Fred. So that brings us to the end. If you want to find out more about these various topics, there's a great deal more that can be learned if you're not totally shelled by all that fountain of information I just laid on you. The job control page in our wiki is the place to start. There's numerous other pages pointed to from there. The commands qsub, qstat, qhost, and qalter, and qdel, qdel's pretty simple, have man pages on the system if you want to read about those. The other things like qsum, showq, memslots do not, because they're local, custom-written utilities that don't have man pages. If you run into a problem, you know the email to write to, support@ace-net.ca. And oh, there's an old link to a wiki page that probably doesn't exist anymore. I should delete that from the slides. Okay, that brings us to the end of the presentation materials. So we